So now we're going to talk about what determines acid strength. Okay, so there's a couple things that we can take a look at. The first one is we can look at trends. There are different trends based on the type of acid that we're looking at, and we can memorize and understand those trends and then rank acids accordingly whenever we see them and identify them that way. The other way is by using Ka. So if we have strong acid, 100% dissociation, we actually don't have an equilibrium, so we don't have a K constant number because there's no equilibrium present. If it's a weak acid or weak base, then we do have an equilibrium present and we can have a K number, a Ka for an acid dissociating or a Kb for a base dissociating, and we can look at that number because it would be products over reactants. If it's a really high number, that means we have a lot of the acid or base dissociating over to the product side, which would give me a higher K number, and that would tell me it's a stronger acid or base. For right now, we're going to start out just looking at different trends. So to recap, we want to think about, what makes an acid strong. So if we think of the definition of strong acids completely dissociate. So they easily can dissociate into their ion form. Okay? And so strong acids easily donate to H+ and dissociate into their H+ ions. Okay? And so our previous example that we looked at was looking at, what side will the equilibrium lie to. The acid-base reaction always goes to the direction of the formation of the weaker acid and weaker base, conjugate acid-base species, and that's because the stronger acid or base wants to dissociate. So it will always lie more heavily to the weaker side. Okay, so there's a couple different types of trends we're going to talk about. The first type of trend is for binary acids. So binary acids mean that we just have one, sometimes two hydrogens, if we're looking at hydrides, so a hydrogen bound to some atom here, okay? And usually there's no oxygen present for binary acids. We have a specific scenario for oxyacids, which do have oxygens in them, okay? So we're looking at an example that's something like this, so hydrogen bound to some type of atom here. All right, and so if we look on the periodic table for electronegativity, we know as we go over to the right on the periodic table that electronegativity increases. And so usually those atoms are more electronegative, meaning they're withdrawing electron density towards themselves, meaning they're going to have more partial negative charge, and we're going to have partial positive charge left on the hydrogen that's bound to it for the acidic proton. And so what we do is we end up making a polar bond. We have a difference in electronegativity, so we have a polar bond. Okay, so the trend on the periodic table for binary acids when we're comparing one to another, as we go to the right across the periodic table, the acid strength increases. Okay, and as we go down the periodic table, the acid strength also increases. Okay, and we want to ask the question, why? Why does it increase as you go to the right on the periodic table? And the reason for that is because we have an increase in electronegativity. So as we go to the right on the periodic table, the electronegativity increases, therefore the difference in electronegativity between the two atoms with that bond will also increase, and it makes the bond more polar. Okay? When the bond is more polar, that means the electrons are more heavily residing to the atom that is more electronegative, so that hydrogen can easily be taken away by a base. Okay, so it's easier to lose that proton. It doesn't really care if it loses or not because it has the electron density over here to help make it stable. Okay, and so that kind of alludes to it being stronger because strong acids dissociate. So whenever this atom is more electronegative than that, it doesn't really care if it loses it or not because it's more stable, and that's what strong acids do. They can easily get rid of that and donate that proton. Okay. As we go down on the periodic table, why does the acid strength increase? If you think about back into the last semester, the size of atoms as you go down the periodic table also increases. So they have, more orbitals, they have more electron density, where those are residing outside of the nucleus, okay? And because of that, it makes the HX bond weaker, okay? So this hydrogen and these electrons here, they're so far out, because this is a really big, huge atom here in this example, that it's not held. They're not held very tightly in there, because it's one of the outer orbitals. That's where the electrons are going to go when it forms a bond in the valence. So it's really far out from the nucleus, and they're not held in very tightly, so it can just easily be taken. Okay, so the hydrogen is held very loosely because, again, those electrons sharing is in that valence shell really far out from the nucleus, because it's a big atom, lots of orbitals, and it's easier to lose the proton from the bond there, and therefore that makes it a stronger acid. Okay, all right, so let's just do a couple examples here. Take a look at which is the stronger acid. We're going to compare hydride. So I know that this is not specifically an HX with no oxygen here, but when we look at, if we just look at the oxygen and the fluorine compared to each other, we have to have, you know, two hydrogens there for it to be a neutral species there. So if you take a look at figure 16.4 in your textbook, that's page 692, there's a table there that kind of sets up the different hydrides that we're just looking at the examples here for, to help rank and compare. All right, so between H2O and HF, which of those is the stronger acid? And so you probably would want to pull out your a periodic table here, okay? And so we would look at where is oxygen and where is fluorine. So oxygen and fluorine are right next to each other, and fluorine is more to the right on the periodic table, so it's more electronegative, so this bond is going to be more polar, and this hydrogen can more easily be dissociated from it than the oxygen. And so this one, HF, would actually be more acidic than a water molecule. All right, H2S and HCl, so comparing the difference between sulfur and chlorine. Right, we want to look at where the position is on the periodic table. And so here, let me see, here is sulfur and here is chlorine. Right, chlorine is more electronegative, it's farther to the right on the periodic table, and so it's going to be stronger. And then if we look at the example, well, now let's compare HF to HCl and see which one of those is more electronegative. All right, and so again, we would look at the position of them on the periodic table. Here's fluorine and here's chlorine. Fluorine is higher, chlorine is lower. So as we go down the periodic table, chlorine is going to be larger. So that hydrogen, the electron density from the hydrogen is held more loosely, and it could be more easily taken, which makes it a stronger acid. So HCl is stronger than HF. Okay, so the second trend that we're going to talk about when we're looking at acid strength is oxyacids. Right, so an oxyacid is a molecule that contains a hydrogen bonded to an oxygen atom. So if we just look at this generic structure here, we have a hydrogen bound to an oxygen, and then the oxygen is usually bound to some other atom. And this other atom we're going to call Y, and it can be bound to a couple different extra additional atoms, maybe bonded to the Y. Right? So we just take a look at the hydrogen and oxygen. Oxygen is more electronegative than hydrogen, and so we have a difference in electronegativity. And the strength of that bond is going to be the same explanation that we talked about for a binary acid in terms of polarity. So because oxygen is more electronegative, we have a partial negative, it's pulling electron density from the hydrogen there to the oxygen, and this makes the hydrogen be held very loosely, so it can more easily be donated, which would make it a stronger type of acid. Okay, so the more polar the OH bond is, the easier it is to remove the hydrogen, the stronger the acid will be. Okay, this hydrogen here is always the acidic one that's bound to the oxygen atom. Okay, a couple different notes about Y. Okay, so the more electronegative that Y is, okay, compared to the oxygen, the more acidic the hydrogen will be, meaning the more easily it can be removed as well. So here, if we just take an example of HOCl, HOBr, and HOI on the periodic table, right? Chlorine is most electronegative here. Electronegativity is over and up on the periodic table, so chlorine is more electronegative. Therefore, this hydrogen is going to be the most acidic and be able to dissociate the easiest. Now these are all weak acids, but this is going to be the stronger of those weak acids there. Okay, another thing about Y is the more oxygen atoms that are attached to the Y, the stronger the acid. Okay, so usually these other bonds here on the Y are other additional oxygen atoms. Okay, so the more oxygen atoms on the Y, the stronger the acid becomes. And again, this is because those additional oxygen atoms are pretty electronegative, and they withdraw electron density away from the Y and also pull more of the electron density from that hydrogen and make it more acidic and easily be able to be dissociated. All right, so if we compare HClO4 and HClO3, these are the structural diagrams of the molecules. So this is perchloric acid. We know that to be a strong acid by definition. And HClO3 has just 3 oxygens bound to it. So the Cl is the Y in our example up here. And this is the acidic hydrogen. Okay, so the more oxygen atoms attached to Y, the stronger it is. And so HClO4 will be stronger because it has more oxygens. It's pulling more electron density away from that hydrogen and making this bond very weak and polar, so it can be dissociated very easily. And then compared to just HOCl. So this is the strongest, the next strongest, and this is the weakest. If we look at a couple other examples here, H2SO4 versus H2SO3. So by definition, again, we memorized our 6 strong acids. H2SO4, we know sulfuric acid, that is a strong acid. And again, if we compare that to H2SO3, we have 4 oxygens compared to 3 oxygens based on the explanation here, right? That one is the stronger. And then HNO3, nitric acid versus HNO2. We have 3 oxygens compared to 2 oxygens. And again, this is the stronger of the 2. And then the last example here, H2SO4 versus HClO4. So both of those are strong acids, but still one of them is going to be slightly stronger than the other. Both of them will completely 100% dissociate. However, one is a little bit stronger classified than the other. Okay, so we need to use our comparison of our trend between sulfur and chlorine. Since they both have the same number of oxygens, and they then we're going to compare the sulfur and the chlorine based on electronegativity, which was one of the binary trends. So we have sulfur here and chlorine here. So chlorine is more electronegative, and so therefore it's going to be pulling more electron density away from the hydrogen, and therefore it will be stronger. Okay, so now we're going to talk about the third trend that we can use to help predict strength of acid. The first one was binary, the second is oxyacid, and the third is a type of other acid called polyprotic acids. These are acids that contain more than one acidic proton. So we're going to take a look at a handout I gave you in class that looks something like this. Okay, so if you pull that out and follow along with that, we're going to go over that here shortly. Okay, so sulfuric acid is one of the 6 strong acids, and that was an example that I put in a separate class. that has more than one acidic proton that can be dissociated from it. Okay, so polyprotic acids, they are stronger than their corresponding anion. So if we take a look at sulfuric acid here, H2SO4, that one proton, either this one or this one, can be dissociated. That is the most acidic, the first proton that gets dissociated off of there, and it is stronger than its corresponding anion. Okay, another acid that is strong, but is considered a weak acid, but it's one of the stronger weak acids, is phosphoric acid. And so this is the structure of it here, and it has 3 protons actually, 1, 2, 3 hydrogens that can be dissociated again and again, and actually then we can even go to PO4 3-. Up here we can dissociate that proton, and we can go to SO4 2-. It's really hard to remove that last proton there, but you can do it under enough basic conditions. Okay, so why is it harder and harder to remove a proton as we go to the corresponding anion? And the reason that it is because, as you can see here, every time we remove an H+ positive 1 charge hydrogen from the acid, we are becoming more and more negative. And so it's really hard to remove a proton from a negative charge, because this negative charge puts a lot of destabilization and makes it unstable, makes it really high energy. So it doesn't necessarily want to go to that structure and lose the proton. Okay, so now we're going to take a look at the handout, the polyprotic acid handout that I gave you. And so the first example is sulfuric acid, which is what we just took a look at on the board. And we can see here in the reaction, the first reaction equation with water, right? It's a strong acid, so it's 100% completely dissociating into its ionic forms, right? And so here is the dissociation of the first proton forming the HSO4-. And then that proton can be removed, this second one, right, because it has 2 protons here. So in the second equilibrium, we have the dissociation, and this one here is only partial. So this is 100% dissociation of the first one, and we have an equilibrium occurring here because this is no longer a strong acid. This is a weak acid. So we have a equilibrium occurring here, and we can remove that proton right there, forming the SO4 2- anion. Right? Another example, this one here is a weak acid, carbonic acid, so that was strong acid. Now we're going to take a look at weak acid, carbonic acid. So here's H2CO3. The first proton is being dissociated. However, this is already a weak acid, so we already have an equilibrium occurring here. We can remove that proton. And then again, we can remove the second one from the HCO3- bicarbonate ion and form CO3 2-. So one thing that I want to point out here is, because these are weak acids, all right, we have equilibriums occurring, we have Kas that are associated with them, right? And the Ka that we're going to talk about here shortly is an indicator of acid strength, right? So remember, K is equilibrium constant. That's equal to the concentration of products over reactants. So that would be the concentration of these products over these reactants, and you would get a number, and that number tells us what side the equilibrium lies to. Now both of these numbers here are relatively small, but this number, the first dissociation of the carbonic acid, is larger than the second dissociation, right? And what that means is the first dissociation lies more heavily to the product side than the second reaction here, because it's smaller and there's not quite as much of this proton that is being dissociated off, okay, here, because it's less, so there's more on the reactant side. Both of them are heavily on the reactant side because these numbers are less than 1, but this one has just a teeny bit more that's dissociating from this acid here to the product side. So there's just a teeny bit more products here in the first dissociation. And that tells us that the first proton is always more acidic, okay? Take a look here at phosphoric acid, which was our second example that I used on the board just a short while ago. And this has 3 protons that can be dissociated. So the first proton
from H3PO4 dissociates off. And again, this is a weak acid, although it's a relatively strong weak acid. So this proton gets dissociated, forming the H2PO4 ion, and we have a Ka associated with that. And then we can take this one and remove it again, take that second proton off, right? Forming HPO4 minus, and we have a Ka associated with that. And then we can just keep making it more and more basic. If we're titrating this acid, we can just keep adding more and more base and finally get this third proton now to come off, forming the PO43 minus ion. And again, if you take a look at the Kas, you can see as you keep removing the proton, right, the respective anion that we are removing the proton for is becoming weaker and weaker because it's not dissociating very much because this number is becoming smaller and smaller. It's not dissociating much over to the product side here. So again, this just kind of confirms the fact that the first proton that is removed from the acid is the strongest, and because here this number tells us we are dissociating more, we have a larger number on the product side than we do on the reactant side. Here. So we can use Ka as an indicator of acid strength. So always the first dissociation, Ka1, this would be Ka1, Ka2, Ka3, is always larger than the next proton that's being removed. Okay, so diprotic acid loses the first one easier than the second because it is stronger and it will lie more heavily to the product side. And a triprotic loses the first and the second much, much easier than the third respectively. Okay, and again, this is the explanation here that we talked about earlier because it's harder and harder to remove a proton as you're forming more, and from here to here you're forming more and more negative charge, so it's harder and harder to do that, and the acid does not want to do that. That's why the number goes down.
Okay, so now we're going to talk about our last point for determining acid strength. We first talk about trends, binary oxyacids and polyprotic acids. Just understanding and memorizing the trends, we can predict acid strength. The last way, and probably the most common and useful way for determining acid strength, is by looking up or knowing the Ka number for a weak acid. So the Kas are either given to you in a problem or on an exam, or you can look them up in the back of your textbook. There's an appendix table that lists all of the Kas for various weak acids, and there are also a couple tables within the chapter you can look up if they're not given to you. For example, in a homework problem, sometimes they won't be given to you. Okay, so Ka. Ka is also used to measure a measure of the relative strength of weak acids. Okay, it will tell you how strong a weak acid is, right? So what is Ka? So kind of talked about it a little bit already, particularly when we were just talking about the polyprotic acids. Okay, K is an equilibrium constant. Okay, and so the Ka, the A just means that it's an acid dissociation equilibrium constant. Right? Strong acids do not have equilibriums, right? Because they 100% dissociate. There's no equilibrium occurring. Therefore, the strong acids do not have Kas associated with them, right? Okay, no equilibrium exists. All right, so if we just take a look at a generic acid that's dissociating HA, okay, just a generic form, we have some proton attached to some anionic species part of the compound or of the original acid molecule, okay, and this proton will dissociate, right? The oxygen will take that proton, and we form the H3O plus ion and A minus anion. All right, if we write a K, equilibrium constant for this particular reaction, we're going to have concentration of products over concentration of reactants here, right? And we learned previously that pure liquids and pure solids do not appear in the equilibrium constant because they are much, much higher concentrations than the other species in the reaction, so we omit them because their concentrations are not going to change with respect to the others in terms of significant figures when we calculate them. Okay, so the water concentration, actually pure water for pure liquid, the concentration is about 55.555555 molar, okay? And so these other species that we're actually going to be calculating the concentration of H3O plus and A minus are always at really, really, really lower concentrations, like 1 times 10 to the minus 4th times 10 to the minus 7th times 10 to the minus 10th. And so that's many, many, many more decimal places out from this water molarity here, and it's not going to change this number significantly at all. Okay, so that's why we treat it as a constant. So we're going to treat it as a constant, and if I put that 55.55 molar in here, and I multiply that over here to the K constant number, okay, then I just have what's left over here on the product side. So this 55 times the K constant, we then convert that and give it a new notation, and we call that Ka. So that's the equilibrium constant for an acid, has incorporated that 55 constant number for water in there. And so it's just H3O plus times the A minus ion concentration over the original HA acid concentration. Okay? All right. So there's another thing that we want to talk about briefly and identify and define because we will use this interchangeably with a Ka number when we talk about acid strength. Okay, and that is percent ionization. So if you have an acid, for example, a strong acid, 100% dissociates over, right? That strong acid, 100% dissociates over, so it's strong, right? That's the definition of a strong acid. So the higher percent that an acid, a weaker acid, dissociates over, the stronger it will be, the more like it will be a stronger type of acid, the higher that number is. Okay? So this percent ionization is just how much the acid turned into its ions, how much of it dissociated. Okay? And so we would calculate this from an ice table, how much the acid ionized, which would be how much it ionized here, how much it turned into the H3O plus ion, okay, that the water got ionized actually, okay, and we would divide that by the original concentration of the acid that we started with. So we have a whole bunch divided by the original, then the higher the percent we would have, okay, of the acid being ionized. So that just turns out to be H3O plus concentration at equilibrium. So we'll have to do an ice table, right, if we don't know that information, and divide that by the original acid concentration that's not ionized initially times 100%. Okay? So if we take a look back at Ka, what does Ka mean? Just like in our traditional equilibrium that we talked about, the higher the Ka number, right, the more products we have made, it lies to the product side. The lower the Ka number, that means we have more reactant. And in terms of acid, it would be the less the acid dissociated, right? So the higher the Ka number, that means we have more products that have dissociated into ions, and that would be stronger type of acid based on the definition. So it would be dissociating more, so the stronger the acid is, and then more of this that would be forming, more of the H3O plus that's forming, that would give us a higher percent ionization as well, okay? And a lower Ka number, that means that we're going to have a large amount of this HA on the denominator, a very small amount that's dissociated, so not very much of the acid dissociated, small amount dissociated, weaker the acid is based on definition, and therefore we would have a smaller percent ionization number. Okay, so just like we talked about for Ka, for a weak acid dissociating, we also can write the same thing for a base dissociating and write Kb. So a base dissociating, instead of using the generic form, I'm going to use the example of ammonia here. So NH3 plus water forms the ammonium ion, NH4 plus OH minus hydroxide ion. Okay, and if I were to write the K equilibrium constant for that, that would be concentration of products over reactants, right? Again, water is a pure liquid, so we're going to treat that as constant. If we put the 55.55 molar in there, then that term times Kc becomes Kb, all right? And then we just have concentration of products over reactants, all right? The same meaning of Kb applies as it did respectively to Ka, and so the higher the Kb number, right, the more the base has dissociated, the more hydroxide ions you're forming, the stronger the base will be, the higher the pH would be. And the lower the Kb number means that you have a lot more present in the reactant side of the base, and it did not dissociate, so you don't have very much OH minus ions forming, the weaker the base. Okay, so now I just want to take a few minutes and talk about a few notes about Kas and Kbs. Okay, and this will come particularly important whenever we're solving problems. Sometimes you'll be given a base and they give you the Ka, and you need to use that information to still solve the problem, or vice versa. You're given an acid and you're given the Kb of it. Okay, so just a couple things here. For example, again, we have our acid, our generic acid equation, Ha plus water forms H3O plus and A minus. Okay, if I write the equilibrium dissociation constant Ka acid for that, this is the Ka in the forward direction. So my Ka would be typically what we just learned, concentration of the products over the reactants here, right? But I can write the Kb for this acid, right? The Kb is the reverse of it because this is the conjugate base dissociating that direction, right? And so the Kb is the reverse. And so this would be concentration of products over reactants for the Kb. Sometimes it can get confusing. So what we like to do is, just to be careful, is to go ahead and rewrite the conjugate base as a reactant. So we can just move these terms here as reactants over products here and then write the Kb. So that would be concentration of products. And again, we're omitting the water, it doesn't appear, over concentration of reactants here, and that's the Kb. If you take a look at the difference between Ka and Kb, you can see that they're just the inverse of each other. And so if you were given the Kb for an acid dissociation or the Ka for a base dissociation, then you would just take 1 divided by that number of whatever the constant is that they're giving you, so that you can use that when you solve ice table problems and things like that. Okay, if we take a look at a base, okay, so a base here, I'm not going to use the generic formula of base because sometimes I feel like that's a little confusing. So we're just going to use the example of ammonia again that we have been using. Ammonia plus water forms the ammonium ion, NH4 plus, and hydroxide. Okay, so this is a base. It's forming OH minus ions. That's how I know it's a base. And in the forward direction, this would be the Kb in the forward direction. So that's concentration of my products over my reactants. And again, I leave the water out, omitted, because it's a constant. But the reverse of that would be the Ka, right? These are the conjugate acid species, or this is the conjugate acid species of that base, okay? And so I can just take these and rewrite them as reactants here, and be able to easily write the Ka. So it's just concentration of products here, again omitting the water, over reactants here. You can look at this and say, oh, these are reactants and those are products, so concentration of products, right, over reactants here. But sometimes we just like to rewrite it so that we don't get things confused. Okay? Okay, so now we're going to do an example problem where we use the information that we just learned about Ka and percent ionization and apply it to a problem to rank some acids based on that information. Okay, so in this example we have 4 different acids, okay? C6H5OH, HNO2, CH3COOH, and HOCl, and that we're given their Kas. So they're all weak acids. Well, some of them are actually bases, but we're given the Ka information. And the first one here, C6H5OH, is 1.3 times 10 to the minus 10th. The next one, HNO2, is 4.6 times 10 to the minus 4th. And CH3COOH is 1.8 times 10 to the minus 5th. And the last one here, HOCl, is 2.9 times 10 to the minus 8th. Okay, so that's the information that we're given, and the question says arrange the acids in order of 2 things that we're going to rank them. The first one, we're going to rank them increasing in acid strength. So we're going to have the weaker, and then we're going to put them increasing in strength to the stronger side. Okay? All right, so Ka. What does Ka mean? Ka is the equilibrium constant, and it tells us how much the acid has dissociated. So the higher the Ka number, the more the acid is dissociated, the more it lies to the product side, right? Okay, so if I look at these numbers, I say, oh, this one here, HNO2, has the largest number. This is only to the minus 4th, so this is the largest number. So that means this is the stronger of all of the weak acids that are given. So I'm going to go ahead and list this one first on the strong side. So this is the strongest, and then this would be the next highest Ka, so the next strongest acid, so CH3COOH. Can you see that orange on there? I don't think you can see the orange very well. So let me just leave the black the way it is. Okay, and then the next one would be our HOCl, that's to the -8th, and then our last one is to the -10th, so that one did not dissociate very much at all, C6H5OH, okay? All right, so the next question says, now we're going to rank them decreasing the percent ionization. Okay, so remember percent ionization, if we think what a strong acid is, a strong acid 100% dissociates. So an acid that has a high percent dissociation is stronger. And likewise, it also has a higher Ka number because it lies more to the product side. So the numerator on the equilibrium constant will be higher. Okay, so the stronger the acid, the higher the percent ionization. All right, but we're only given Ka numbers, so we can go back up here and do based on Ka, or we can go based on here, assuming that we're correct, and rank things accordingly. That would be the same trend, right? Increase, increase, decrease, decrease. Okay. So instead of just kind of replicating what we have here right down here, let's go back up and just practice using the Ka information and relate that to percent ionization. Okay, so Ka is acid strength, so the higher the Ka number, the more the acid has dissociated, and we've identified as this is the highest number, so this would be a stronger acid based on Ka, and also will give us a higher percent ionization. So we should have a higher percent ionization here. So this HNO2 should go here. Okay, and then following in suit, this is the next highest Ka number, so the next stronger acid, and that would have the next highest percent ionization. So we would rank it here because we're going highest to lowest percent ionization. And then finally HOCl, and then eventually C6H5OH.